Regarding the title of my talk, there's a lot of words in there. Some of them are more important than others, like in any title. It'd be kind of awkward if I rank all the words and their importance, but Bayesian is one of the least important words. So if this is what you're interested in, it will be a little bit disappointing. I use Bayesian in the title because it's just a way of generating interesting cost functions, nothing more. The underlying theory and the underlying rationale of what I'm doing is completely independent of anything Bayesian. And if you can think of other ways to generate the same class of cost functions, it's just as well. And I've done this very thing. Okay, so kind of to begin the basic message here, sparsity and rank. This is a pretty obvious slide, but the idea is these are very related. We all know what the L0 norm is. It's a count of the number of non-zero elements in a vector. And you could write this as a sum of the rank of scalars. So, and likewise for a matrix, you could view the rank of a matrix as the L0 norm of the vector of singular values. So the interesting part is more that if you want to mix these two for more rich type of structures, you can express everything in terms of L0 norms and ranks, or ranks. And then I'm sure you know the most common thing to do is a convex relaxation, so that follows from this. So at the highest level, the general estimation problem I'm going to look at is as follows. We have some observations why these could be a matrix or a vector, and then we have some sensing matrices, a whole set of them, phi sub I. And we want to estimate a set of matrices or scalars. So this set here, x sub I, they could be arbitrary matrices of different sizes, all mixed together and summed up. And the idea is we want to minimize a linear combination of the rank of these things. Many of them could be scalars, though, so you could recover something like compressive sensing. And then we have an affine constraint here. We just vectorize the matrix x sub I, and then we sense them with a bunch of these matrices, and that's it. And of course, you can relax this equality constraint if you want. So here are many of the special cases that have been popularized over, I guess, the last 5 or 10 years, or even longer. The first one is matrix completion. You know, we have a matrix, but we're only allowed to observe a few of the elements of this matrix, and then we want to recover the whole thing. And the typical assumption is that the latent matrix is low rank, which allows us to do such a thing. A second example is robust PCA, and here we have an observed matrix, and we want to decompose it into a low-rank component, which is the typical principal components, but then we also have sparse outliers. And a third example, which is kind of what got me into this whole field, is source localization. This is something that's very popular in the neuroscience community. The idea here is the source space is the brain volume, and you have a lot of activity in the brain, and many times it's correlated, but for a particular activity, it's often localized, especially when you average over subjects. So in the source space, you have all of these x sub I, and these are like brain activity areas. And you can map using Maxwell's equation, if you're doing MEG or EEG, a linear operator that maps it to the sensor space Y. So you put a bunch of sensors outside the head, and you have a linear mapping there, which is actually a very good approximation because it's just laws of physics and Maxwell's equations. And then the idea, though, is you want to go backwards here. I'm not really going to talk much about this application, but there's a lot of interesting ways to apply sparse and low-rank estimation. And we've gotten very good results in this realm. And then finally, we have compressive sensing, which I think everyone is familiar with, even if it's fading in its glory as it once was 5 or 10 years ago. Okay, so the typical estimation recipe is that we know that all of these problems are NP hard, right? So the most common thing is to do a convex relaxation. There are also many greedy type strategies. I won't talk as much about that. But one of the most common things is the greedy relaxation. And we just replace the rank with the nuclear norm. And there's a lot of very elegant theory that guarantees conditions when problems like this, when you replace the nuclear norm, you still get a good approximation to if you were using the rank to begin with. So what I'm going to argue is that perhaps it's premature that we always need to convexify everything. Obviously, I don't want to be dismissive of convex algorithms. They're very elegant theoretically, they're very efficient computationally, but are there alternative types of cost functions that are non-convex that could be better? So we're going to look at, in some sense, this is the whole philosophy of this talk, is a non-convex penalty function, but maybe a slightly atypical type of non-convex penalty. And we're looking for ones that satisfy these two properties. So it's a penalty on the set of these low rank, of these matrices we want to be low rank, and we would like it to approximate the real thing. And by approximate, we mean that we want it to have the same global minimum in the feasible region, and always, not subject to some condition on how structured the measurement process is or other things. We kind of want to anchor the global minimum at the same solution. And once we do that, then we can say, if we accept that we're anchoring at the same global optima, is there a way to smooth out locally minimizing solution? And what is the maximal degree we can do this? And one potential limitation is that no such penalty that can accomplish this you can write in this separable form. So the typical thing when you have various structures you want to estimate is you just put a penalty on each thing and you add it up. But this, when you jump to this, when you restrict yourself to this type of penalty function, you provably can't do this type of thing. So we need another class of penalty functions. And this is where the Bayesian inspiration comes in, is that the separable penalties of this form here are common, but we need something else. So we need a source of inspiration. And some empirical Bayesian models that have been around for decades do this very thing. Even though they've never been marketed this way and promoted in this way, it turns out you can show they do exactly what we want. But the key point here is that the final model justification will have nothing to do with the Bayesian model we started with. It will be completely based on the property of the cost function that emerges from this process. And today the time is a bit limited, so I'm just going to illustrate this via two special cases, robust PCA and affine rank minimization. But I want to emphasize that really the underlying philosophy extends to virtually any problem you can apply a convex relaxation to. So example one is robust PCA. I guess many people here are familiar with it. We have an observation matrix, and we want to decompose it into a low-rank part and a sparse part. So here's the model, the notation. The data is Y. It's M by N observation matrix. And without loss of generality, we just assume that it's a fat matrix. And we want a low-rank approximation, A, B transpose. And there are sparse errors and potentially Gaussian errors as well, small diffuse errors. So classical PCA you could view as a regularized rank minimization problem where you have a data term in the rank, and we all know, and of course if you adjust this parameter lambda here, you will get a solution. You can decide how many singular or principal components you get. And there's a closed form solution via SVD, but of course this is assuming that S equals 0, so there's no significant outliers. But we all know that classical PCA can be completely disrupted by even one outlier. It will give you radically different principal components. So we just append this additional term that accounts for sparse errors. And this factor n here, you could tune it, but the nice way of choosing n here is that it kind of balances these two terms here. It ensures that both penalty terms scale between 0 and n times n. So it's more just kind of for symmetry. It's agnostic to whether you think the solution should be more low rank or more sparse. And of course, this problem, though, is NP hard, so we need some approximate methods. And here's, of course, where the convex relaxation comes in. This n switches to a square root of n for some technical reasons, but basically this is the convex relaxation of the cost function on the previous slide. And the nice thing about it is there's some efficient algorithms, principal component pursuit, a lot of ADMN, many different types of algorithms for solving this efficiently. And there's provable recovery guarantees as well that bound how much error you can have recovering a true low rank and sparse solution. But of course, these require a lot of structure on the support of S and on the singular vectors of X. And in practice, we never really know if these conditions hold. And in many of the applications where people apply robust PCA, I think you can prove that these conditions do not hold. So here's where the Bayesian model comes in. Or should I say the Bayesian inspiration. So we start with just a likelihood function. This is very boring, just a standard Gaussian. And then we use empirical Bayesian priors. So empirical Bayes just means that the prior has parameters that you don't know, and you're going to estimate these parameters from the data. So what do these priors look like? Here on S, we have an independent Gaussian distribution on each element of S. And each one of these parameters has a variance associated with it, an unknown variance. So you can imagine that if this variance were very small, it would favor this coefficient to be near 0. And that's where the sparsity will ultimately come from. And then likewise for this, the low rank part, we have an unknown covariance. And we just also have a Gaussian with this covariance in there. And as this covariance here becomes degenerate, it starts favoring a Gaussian that collapses to a degenerate subspace. And actually for the algorithms we use, we also can make a symmetric version of this prior. So right here, you can imagine it depends on whether you define your data as Y or Y transpose, which would affect here whether you have X transpose psi inverse X or X psi inverse X transpose. So you have this asymmetry. But there's a way to make a symmetrized version of this that's quite effective. So these are the two priors we use, very simple. Yes, I will come to that. So good question. So basically, for now, though, I'm assuming that, say you know those variance parameters and covariance parameters. For the approximate inverse inference for your estimate of the unknown X and S, it's very simple. Because if you have these, everything is Gaussian. So you have a posterior distribution that's Gaussian, and you have closed form posterior moments. So we will choose the mean of X and the mean of S as the approximations to X and S. And so now, speaking to your question, we just need to estimate these hyperparameters. And basically, all we've done here is we've shifted the burden of the algorithm to estimating variances and covariances instead of estimating coefficients directly. And the cost function we use, which can be minimized with very simple update rules and the EM algorithm, actually there's many different ways to derive the algorithm. I won't get into that. You can derive it with, you can do algorithms with reweighted nuclear norm, L1 norm, reweighted L2 norm. There's a huge set of algorithms you can use to minimize it. But at a very simple level, you can use EM to do this. So the idea from the empirical Bayes is, at this level, you treat the S and the X as nuisance parameters, and you just integrate them out. And once you integrate them out, you get a cost function that depends only on this psi and this gamma. And once you have those, then you go back to here and estimate the means, and you're done. OK, so the final estimator you get like this is kind of interesting. So you can show that the posterior mean X and posterior mean S are the argument that minimizes this optimization problem. So this penalty function here is a little bit strange. You can express it, there's no closed form expression, but it has this variational expression that depends on these variances and covariances. I won't really have time to go into the details of this penalty function, but one thing you can notice is that this variational penalty depends on the covariance psi and the covariance, and the variance is J. So this gamma bar here is just taking the diagonal of the original gamma. Let me just back up and so gamma sub J is the jth column of this gamma here. And when you diagonalize it, that becomes this capital gamma bar. So you can imagine this is a concave, non-decreasing function of the singular values of this matrix. So this penalty here is favoring covariances and variances going to 0, which then is the ultimate source of the sparsity and low rank that comes from this model. But even though you can't express this whole thing in a closed form, you can still analyze it and analyze some of its properties. And there's an interesting connection. So I derived this maybe from a circuitous route, with this empirical Bayesian stuff, but actually there's an intimate connection just with the original robust PCA and the convex relaxation. So here's the penalty function I showed you before with this log determinant term. And if all you do is replace this log determinant with the trace, that's all you do, and you go through a little bit of math and manipulate terms, the penalty function you get decouples, and it breaks down into the nuclear norm plus the L1 norm. And the interesting thing is when you do this, you also get the kind of theoretically motivated weighting factor just naturally pops out. So really, empirical Bayes, all it has done is replace the trace, if you go backwards, with the log determinant. The difference, though, is when you put the trace here, everything separates. But when you put the log determinant here, everything couples together. And this is quite important. But the other point I should mention is that this viewpoint of expressing penalty functions in this variational form in terms of covariances and variances is a way to generate virtually any penalty function that is used in the literature. And there are some theoretical reasons why generating penalty functions in this kind of variance-covariance space is more advantageous than generating them in the original primal space that everyone is used to. For this talk, I won't get into that in depth, but there are a lot of reasons for this. So here's just a couple of properties of this GEB, which is the empirical Bayesian penalty function. First, it's a concave function of the magnitudes of each element in S, and a related thing for the singular values of X. So it does promote sparse and low-rank solutions. But this in and of itself isn't very interesting because we already know lots of penalty functions that are concave, non-decreasing in this same respect. So really, we haven't gotten anything here. The interesting thing, though, is that it's non-separable. There's no way to break it down into this form. And this is the key property that makes it successful. So here's just one type of analysis. We're working on some stronger forms, but here's the type of thing you can show for this cost function. So we're going to assume that E equals 0, so there's no Gaussian diffuse errors, but you can extend it to handle this case as well. But for simplicity, we're just going to use the canonical robust PCA model. So all of the noise is sparse errors, gross outliers. So problem P1 is just a rank term and the typical sparse term weighted by n, so that these are two perfectly balanced. And then we have the constraints here. And all we're going to do is replace this penalty, which is NP hard to optimize, with what we get from empirical Bayes. So what can we say about this replacement? In an ideal world, we would like conditions where we can guarantee that using this penalty function guarantees that we recover the true solution. And we can't quite do that for the general case, but we can say things like this. First of all, P1 and P2 always have the same global optimum. So this is a nice thing. This speaks to my original theme that we want to anchor whatever alternate penalty or cost function we use, we want to anchor the global optimum at the solution we really care about. But the more interesting part is that P2 is smoother. It has provably fewer local minima than any possible problem that can be written in this separable form that also always globalizes P1 for all y. So this is where the interesting thing comes in, is that we really do get provable smoothing of local minima. And another nice thing, I won't go into it in detail here, but you can actually implement this algorithm with an iterative reweighted form of the convex robust PCA. And when you do this, you can guarantee that the solution will always do as well, and it can never do worse, but there are cases where it will always do better. So what is the intuition? There's many ways to kind of break apart this cost function and look at what it's doing, but at the highest level, the intuition of why this non-separability works better is as follows. So if you take any penalty function that can be broken into this separable form, and you want to guarantee that it has the same solution as rank plus L0 norm,
you will provably enter a local minima whenever the rank is less than m, so m is the smallest dimension of y. Or if the jth column of S, the L0 norm of it, is less than m. So if either of these conditions hold, you'll get stuck in a local minima where the rank can never go up again, and the L0 norm can never go up again. So there's a combinatorial number of these types of local minima. But in contrast, when you use this weird empirical Bayesian penalty, you don't have this same problem unless the sum of these two is less than m. And this is a huge difference. So just a quick empirical evaluation. And first of all, I just want to mention something very important about how we generate the data. Because I've seen a lot of very impressive phase transition diagrams for non-convex algorithms. And invariably, you have to look in the details of how they generate the data. Because when you run a convex algorithm, the magnitudes of the outliers and the singular values don't make a difference. But when you run non-convex algorithms, the magnitudes make a huge difference. And so you have to look. This is a typical slice of one column of a matrix Y that has a low rank component and sparse outliers. And you can see here it's very obvious the location of the outliers. So this is a very easy case because if you run many types of non-convex algorithms work well because the outlier locations are obvious. So the problem almost collapses to like a matrix completion problem where you know which entries are missing or corrupted. The hard case is here, where you look at a slice of the observation and you have no idea where the outliers are located. And for the experiments I'll show, this is exactly the data we use to generate our problem. And I think it's important to make this distinction because the phase transitions plots you see are often, they can be misleading. And I think the main reason people like plots like this, one, the algorithms work well, but also the signal to noise ratio here can actually be below 0 when you make huge outliers with huge magnitudes. But in fact, the counterintuitive part is that the bigger you make the outliers, the easier the estimation problem becomes. So here's a typical phase transition plot we get for this hard case. And here's the recovery region of robust PCA, the convex version. So along this axis, we have the outlier ratio, the percentage of entries that are corrupted, and along here we have the percentage of full rank. Now here's convex matrix completion where we know the locations, the missing entries. So obviously the phase transition expands dramatically. Here's one of the top performing non-convex algorithms and you can see that on this hard case, the phase transition, you almost don't gain anything over the convex algorithm. And this is something I've seen it again and again. On the interesting problems, many algorithms don't do better than the standard convex thing. But when you look at convex empirical Bayes, the phase transition plot basically matches the convex algorithm, even though it's at a huge disadvantage. Here we have no knowledge of where the corrupted locations are. Here you have perfect knowledge of so you get a huge jump when you do this empirical Bayes. There's an application we do to photometric stereo. I will skip this and just quickly mention some results on affine rank minimization. So here, this is the matrix recovery, just a single matrix X, and you have affine constraints. And there's one extra kind of property of this model that is illustrated by this special case, which is nice to mention. So existing algorithms typically are of this form. You have the same constraint set. You have a sum function f on the singular values of the matrix. And it's a separable function of these singular values. And there's a theoretical limitation when you jump to this class of functions. And invariably, when you use this type of function, they're very sensitive to the correlation structure. The simple case is here where the off-diagonal energy is small. This is the hard case, which mirrors something like what you see in compressive sensing. And how would you compensate for this type of correlation structure? The simplest motivational example would be, what if you want column norm invariance? So the L1 norm is very sensitive to the column norms of phi, but if you take each column of phi, and here nu sub I, eta sub I is the L2 norm of one column of phi, and you weight the L1 norm penalty by this, it's invariant to column norm. So this motivates a penalty function then that depends on phi transpose phi
to compensate for this type of correlation structure. And if you go through the same type of marginalization and empirical Bayes, you get a cost function that looks like this, and it depends exactly on this property, this quantity, phi transpose phi, and it compensates for correlation structure. So this is the last slide I'll really talk about. What are the contributions of this substitution? So if instead of putting the rank here, or the nuclear norm, you put the empirical Bayesian penalty function, here you get a global optima that always has minimal rank, but fewer bad local minima. And for this reduced problem, we have conditions that there are provably no local minima. And in practice, we have tried a zillion different empirical experiments, and this algorithm works as well as any possible algorithm, where the number of degrees of freedom in X equals the dimension of Y. So there's, at least in a vast swath of empirical examples, it's impossible to beat this algorithm. And I think this is the first algorithm that can demonstrably do that. So I think my time is up, and that's it.
Thank you. Are there any questions?
You talked about empirical Bayes methods, and they're widely appealing, but one of the known drawbacks is the fact that they are the standard tools for assessment are at best quite misleading, precisely because you're replacing unknown hyperparameters by the estimates, and they don't recognize that these are estimates. They pretend that they're real things. And I wonder how that, and Jim Berger discusses some of that in his book, I wonder how that plays out in your work.
So if I understand the question, you're asking about the typical criticism of empirical Bayesian methods. And I think at a high level, these methods are valid. But here, keep in mind, we're using the empirical Bayes just as an inspiration. So it goes back to some of the statements I made at the beginning. The properties of the cost function we get are independent of all of that. They're independently justifiable. So while what you're saying may be true at a high level for arbitrary empirical Bayes, in this restricted context of low rank and sparsity, it doesn't really apply, because the cost function property itself is what dictates the performance. And here I think we have some rigorous theory to support what we're doing.
Thanks.
Sure. Yeah, it does make that's a good question. So the question was about whether you parameterize via covariances or precisions. And it depends on the type of estimate you want. So we're actually now looking at precision models. And the precision parameterization allows you to estimate a completely different type of structure. So it's not obvious when you just look at the variational structure, but when you dig into the details a little bit more, there's a whole different class of inverse problems you can solve when you parameterize via precisions. Yeah. I don't have time to go into the details, but.